What exactly is the difference between an ion, an atom, and an isotope? Well, one thing you must know to understand this is that atoms, ions, and isotopes are all different types of an element. Element is the umbrella term, sort of how Toyota, Tesla, and Jeep are all types of a car. If I told you that a car has four wheels, that would by definition mean that all three of these brands also have four wheels because they each belong to the category of car. Similarly, whatever property belongs to the element therefore applies to all types of that element. Now, whenever we talk about elements, we're referring to the periodic table of elements, such as beryllium, sulfur, and sodium. Let's single in on the element of phosphorus. If we look at its elemental box, we see that phosphorus has a 15 in the corner. This means that phosphorus's atomic number is 15. And what's so important about this is that atomic number is synonymous with the same thing as the number of protons. So by its very nature, phosphorus has 15 protons. So applying our logic from earlier, because the element of phosphorus has 15 protons, so too do the atoms, ions, and isotopes of phosphorus. And this is unique and distinguishing element to element. So for example, oxygen is the element with 8 protons. So all of its atoms, ions, and isotopes each by definition have 8 protons as well. Thus, for each individual element, atoms, ions, and isotopes share the same number of protons. But this is a video about the differences between them. So what is the difference between atoms, ions, and isotopes? Well, the answer to that question is in defining each of these terms. Firstly, an atom is any element wherein the number of protons and electrons is equal. So all three of these on the left represent an atom, whereas the three on the right don't. If protons equals electrons, it's an atom. If they're not equal, it's not an atom. Specifically, if there's an atom with 8 protons and 8 electrons, it's an oxygen atom. Neon atom if it's 10 and 10, and iron if they're both 26. But what about the neutrons? We haven't mentioned anything about this subatomic particle when talking about atoms. Well, it turns out that because the definition of atom makes no mention of neutrons, neutron count is irrelevant. It doesn't matter in determining if something is an atom. All 4 of these subatomic particle combos are atoms of iron solely because the protons and electrons are equal. Neutrons may or may not be equal to the other two, but as I said, that doesn't matter when defining it as an atom. Conversely, if atoms are elements where the protons and electrons are the same, ions are elements where protons and electrons are not the same. They're not equal to each other. If we revisit an earlier slide, all 3 of the non-atoms on the right side were simply ions all along. And as before, we have an atom of oxygen, an atom of neon, and an atom of iron. And remember, the number of protons is what determines the element of interest. So what we see on this slide is an atom and an ion of each of these respective elements. For oxygen specifically, because it must always have 8 protons, to be an ion, we could have a variety of electron counts as long as it's not equal to 8, in which case it would be an atom of oxygen. So we could have 6, 7, 9, 10 electrons, usually something close to 8, but never exactly equal to 8 if it's an ion. And as with atoms, the definition of ion makes no mention of neutron count, so again in theory it could be any positive count of neutrons. I say in theory because while we see an atom on the left and an ion on the right, neither are going to exist in nature, because having 9 times as many neutrons as the others is way too unstable, even though they both technically fit their respective definitions. Looking at both of the atom and ion definitions side by side, you may have noticed something very interesting, and that's that atoms and ions already account for all element possibilities. In other words, no matter what combination of protons, neutrons, and electrons we have, it must either be an atom or an ion. This is just like flipping a coin, as it's either going to be heads or tails, never both at the same time, and there's no other outcome where it's neither heads nor tails. Analogously, an element is either an atom or an ion. There will never be an element that won't be either of those two categories. That means that before even knowing what an isotope is, we know that it must be paired with atom or paired with ion. Isotope is not a separate third category and instead simply adds another layer of information. And the information an isotope adds is that it specifies how many neutrons the element has. Let's look at one of our examples from earlier where we have an atom of iron as it has an equal number of protons and electrons. We also specify it as an isotope of iron with 24 neutrons. But more formally, we would call this isotope iron 50. But where did we get this 50 from? Well, it's actually the sum of the protons and neutrons. 26 protons plus 24 neutrons equals a count of 50. What about this example right here? It's an ion because there's an uneven number of protons and electrons, and it's an isotope with 24 neutrons, which also means that it's iron 50 because, again, we get that number by adding the protons and neutrons together. So both the ion and atom of iron are iron 50, but we have to find a way of differentiating between the two without simply spelling out each of the subatomic particle counts. And we do that by using full isotopic notation, which you must know, and there's a video on your screen and in the description which walks you through just that.